Coming up on Leading the Charge.
If we look at the largest dam in the US, which is the Grand Coulee Dam in Washington, its output is about 21 terawatt hours per year. And when we look at the consumption, this means that we need about over 1,000 of them in order to satisfy our needs. And if we compare it to, the largest dam in the world, which is the Three Gorges Dam in China, its output is about 110 terawatt hours per year. And this means that we need 250 of them. So you can imagine that, we have a lot of demand for electricity, and we are going to increase in that because we are going more and more in electrification. So this demand can only increase.
This is Leading the Charge, where we talk innovation and insights in the industry of sustainable energy. Leading the Charge is brought to you by POWR2, a global provider of energy storage solutions. Let's simplify sustainability. And now, from the POWR2 studio and broadcasting everywhere from leadingthecharge.io, here are your hosts, Tim Doling and Kevin Sturmer. Welcome to Leading the Charge, where we talk battery energy storage, insights, innovation, and the industry of sustainable energy. My name is Kevin, and I work in the marketing department of a company called POWR2. And with us, as always, is the incredible Tim Doling. He's the Director of Innovation here at POWR2. How are you doing, Tim?
I'm doing great, Kevin. Very excited for this episode, that's for sure.
Yes. Me as well. Many of you are familiar with our power banks and how we talk often about not all battery energy storage systems are created equally, and it's what's inside that counts. Now, a lot recently, when we've been talking about that, we've been referring to our energy control module on the power banks called Advantage. But today, we're going to be talking about the batteries themselves. Lithium-ion batteries are used in electronics from cell phones to, again, our power banks. You probably know that. What you may not know is lithium-ion is actually the umbrella category under which there are many different combinations. It's lithium-ion and a variety of elements from the periodic table. And those pairings, they have strengths and weaknesses based on whatever application you might be using. Now, it would take an advanced degree and years of research to fully understand the intricacies of these combinations. Lucky enough for us today, we're joined by Dr. Wan Si Tang. She's the Director of Research for Novel Materials and New Energy Forms at the Electrochemical Safety Research Institute, which is one of 5 institutes under UL Research Institutes. And we've got a graphic on screen. If you're watching on YouTube or Spotify, go check that out. Welcome, Wan Si, and how are you doing?
Thank you for the very kind introduction, Kevin, as well as Tim. And thank you for having me here today as well. I'm really looking forward to chatting more. And you are too kind with your introduction.
We're excited. We're excited that we have an expert in the house, and we've done our research. You are an expert. You spent years on this. But before we get into those deeper discussions of lithium-ion batteries, I'm always curious because I have a couple of scientists in my family, and I know their stories. But was there a light bulb moment for you when you knew you wanted to pursue a scientific research career?
I fell into research. I never thought I would be a scientist, but I fell into it. And I think it was because I was working on something that was very applicable into the real life for energy storage. We'd like to start the conversation today by talking a little bit about electrification. I'm a scientist, scientists, and we like numbers. So I'd like to start with giving a little bit of numbers for some perspective. So for example, in 2022, we have 8 billion people on Earth, and the amount of electricity consumption was 25,000 terawatt hours. So this is just electricity consumption, not other energy consumption. So 1 terawatt hour is 1 trillion watt hours. So that's a lot of numbers, but what does that mean? So let's compare it to maybe an output of a hydroelectric power station. And I chose this example mainly because it is a sustainable, renewable energy source. So if we look at the largest dam in the US, which is the Grand Coulee Dam in Washington, its output is about 21 terawatt hours per year. And when we look at the consumption, this means that we need about over 1,000 of them in order to satisfy our needs. And if we compare it to, the largest dam in the world, which is the Three Gorges Dam in China, its output is about 110 terawatt hours per year. And this means that we need 250 of them. So you can imagine that, we have a lot of demand for electricity, and we are going to increase in that because we are going more and more in electrification. So this demand can only increase. But electrification is not new. It's something that has been happening since the 19th century. And of course, in vehicle application, we have electric cars, and we also have gas-powered internal combustion engine. But in fact, when we think about electric vehicles, that was around before the internal combustion engines. And one of the examples that I really like to give is a car called La Jamais Content. So when translated, it means never satisfied. So this is a car that was built in Belgium in 1899. And the wonderful fact about it is that it went up to speeds above 60 miles per hour. So this is, more than 100 years ago, this was happening.
Hold on. Pause for a second. 1999, 1899.
1899. So it's over 100 years ago that this was happening. So it's not a new idea or a concept. However, we know that since the 1920s, we've been using internal combustion engines in our cars instead as the energy storage device.
So just briefly, why the break then? If this technology was available in 1899 and it got to those surprising speeds back then, why did that not become mainstream? Why did the internal combustion engine just take over so much more quickly?
That's a good question. I was going to cover that somewhere down the line, but
Okay, sorry.
No, it's of course it's a very good question. Like, why has battery technology taken such a long time to be in cars, right? Mainly it's because it's really a systems challenge. So in a battery, there are a lot of components that go into it, and they all have to work in sync with each other in order to have a good working life. So you can imagine if something goes wrong, then your battery can fail very easily. So thinking about that, there is a big reason why it has taken such a long time for electrification. However, in 1991, the first lithium-ion cells from Sony were produced, mainly for consumer electronics. But that's where I would say the lithium-ion journey really started. The technology that they used was called lithium cobalt oxide as the cathode material. And then EV started making a comeback after that. So we had the nickel metal hydride that was used in a lot of hybrid cars, and slowly we're seeing more and more lithium-ion cells into hybrid and fully electric cars as well. I seem to be talking a lot about how challenging this technology is. I do want to say there are silver linings. I've mentioned 1991. That's when the first lithium-ion cells were in the market. It means that we have over 30 years of experience in this, very new technology. And as comparison, we can think about something similar, which is lead acid batteries. It's a very mature technology. We know how to recycle it. We understand its toxicity. So I would say that, plenty of challenges for lithium-ion, but it doesn't mean that we cannot overcome that. It doesn't mean that there wouldn't be new solutions to improve them.
You got into some of the combinations there. You mentioned nickel, you mentioned cobalt as well. So in our batteries, we use LFP, lithium iron phosphate. What are when it comes to those various kinds of combinations, what are some of the advantages and disadvantages?
Yeah, you probably know the main battery materials, active materials in cells haven't really changed much. And so on the anode side, we have graphite as the main active material. And on the cathode side, it's mainly a lithium transition metal oxide. We usually shorten it, acronym it as NMC because of its constituent metal oxides, which are nickel, manganese, and cobalt. But of course, there are some substitution that can happen within that chemistry as well. And then the other one is, as you mentioned, the lithium iron phosphate or the LFP chemistries. It really depends on the application that you would like for your batteries, why you use different technologies. But for me, these technologies have been around for a while. They've been heavily researched on since the 70s. So they are at this point pretty mature technologies. And for us, as you mentioned, we have novel materials and new energy forms in our name. So we are really looking forward to the next stage of materials that are either being still researched on, or the next 5 to 10 years we may be able to see them in the market. So we're actually a very new team within ESRI, or the Electrochemical Safety Research Institutes. So as you mentioned, UL, we have 130 years of experience in safety science. And recently there was some restructuring. So we are actually under the UL Research Institute side. And together we are working for a safer world. So ESRI in particular, we are looking to advance safer energy storage through science. So traditionally, we have looked at a lot of safety research on battery packs and modules. But more recently, we've started to think about, what about looking at it from the very beginning, looking at it from the materials itself, and looking at the smaller cell capacity level. Because safety has always been like an afterthought. People don't really think about safety of a technology until something happens. So the team has 5 other wonderful research scientists, and we are really interested in 3 main research directions. So of course, safety is on the top of our minds, but we're also looking at new materials. So as I mentioned, the cathode anode materials hasn't really changed much. But there are a lot of them in the research side that people are looking at, including silicon, solid state batteries, lithium metal, sulfur systems, sodium ion. That's a very hot topic right now. There are also divalent ions, for example, magnesium batteries or calcium batteries. And of course, there are always newer cathodes that people are trying to research on for lithium-ion batteries in particular, but they are more for higher voltage applications. But we're also interested in, other energy storage and conversion materials, not just for batteries. Hydrogen storage is making a very strong comeback right now. And yeah, very excited for that. We have learned that we have been very over dependent on fossil fuels, so we should learn how to diversify our energy sources. So not just electricity, not just batteries. We need to look at other sources of energy as well. So that's something that we're interested in. And then finally, we're also interested in the engineering side. So chemistry is one thing, but how do we actually make the batteries? And the way that we've been manufacturing batteries hasn't changed since, actually, as I mentioned, the first LCO cells were made in 1991. So we borrowed actually a lot of technology from the paint and from the photographic film industry. So there is a reason why we are using the same solvents. There's also a reason why they're in the cylindrical cell format. So if you've made electrodes before, I would say you have been watching conductive paint dry on a metal foil. So I like to break it down that it sounds very simple, which is just paint drying. But how do you get that paint to work? I think that's the trick. How do you actually get it to work in a full system? Something that we just started recently is using 3D printing to manufacture a cell. And we're not only interested in building better cells, but we're also interested to reduce the amount of materials used, and so the amount of waste that's generated, that would be less as well. So for us, it's not just safety, but also looking at the materials, chemistry, as well as engineering.
Wow, so much to unpack there. So many questions from that. Right at the beginning, you talked about LCO. I don't hear much about that technology. Is that still being used?
It is still being used, and there are still companies that produce LCO cells. And I believe it's always it depends on your final application. There are always small nuances in the different, even within. So LCO is part of the NMC family, and then within that there are always small nuances, and depending on your final application, you should tune your chemistry toward that application.
Yeah, fair enough. You mentioned, Wan Si, that hydrogen is making a comeback. Has it previously been a mainstream fuel in the past? Because most of the time I'm talking to people about hydrogen now, and they're concerned about its availability, its infrastructure, the fact there's not much of it available. and then the transport and storage, just the volatility of it as a gas and being very flammable. How do I get it from where it is originated to where I can actually use it? So, but you said it's making a comeback. I was just curious about that.
Yeah, so actually when I first started my research, as Kevin has talked about, I actually started working on hydrogen storage materials. So that's where I first got interested in, materials really for a final application. I talked about batteries as a systems challenge. I think hydrogen is an even bigger systems challenge because you are coupling actually different components together, not in a single cell, but in sort of a more on a modular level. So there are, between the two, I think there are more challenges for hydrogen storage versus battery technologies. Not that battery technologies don't have their own set of challenges. In more recent years, there were a lot of research that went into battery, but it's becoming a bit saturated at this moment. And as I said, we do need to diversify our energy sources and not just bank on the particular one. And really, depending on what your final application is, you should be able to tune your source in order to meet that final application.
Yeah, and that's definitely in line with what we've heard around the board, is that going forward, sustainability is not about one solution. It's about a mix of things that are going to be specific to whether you're trying to power a remote location, to trying to power a construction site that's pulling a high draw of electricity, and anything in between, or powering a live event like a concert or something like that. You mentioned safety as a priority for your team, and these are questions we still get. We have people at trade shows come up and ask, are these lithium-ion batteries, can they still catch fire? So can you talk a little bit about safety, go a little bit deeper into that, and how it can remain a priority for everyone?
UL is big on safety, and I think right now what we're seeing is related to battery safety. We're seeing more and more incidences about, fires, thermal runaway, a lot of news articles coming out because of that. And that is true. We've been seeing, more fires from, manufacturing facilities to commercial transport, planes, buses, cars, to within the commercial stores where they're actually selling the batteries. And it goes into, commercial products when we are using them at home. And we're increasingly, because of recycling, we're hearing them in, recycling facilities as well. So, there are a lot of risks to the public, and especially first responders, since they are, the first ones on site. They need to assess the situation. If there is a fire, they need to know what chemistry it is. They need to know how to fight that fire. So it is a very big problem, and the public, they should be asking these questions, and they deserve good answers to those questions as well. So, a lot of this time, safety is always an afterthought, right? The product is in the market, something happens, and they were like, oh, wait, we need to go back to the drawing board and see how we can salvage that situation. But that is a very costly band-aid to think about it at the end. So that's why we are hopefully be able to change that mindset to think about the safety starting from the materials all the way through, the commercialization process. You should have that in mind. Some examples that we've seen, from history is, for example, the EPA, the Environmental Protection Agency, that came about because I think lakes were starting to catch fire. So, these are like afterthoughts. And for example, the ESG movement on environmental, social and governance, these are sort of afterthoughts. So we would like to change that mindset to, let's start thinking about some consequences at the beginning. So one very nice program that we're having with ARPA-E right now, which is under the Department of Energy, we have this program called EVs for All. So essentially, we are working with several different partners from Sandia National Laboratories, from the University of Maryland, as well as Purdue Universities. Together, we're working with different teams that have different upcoming pre-commercialization technologies in order to evaluate the possible failures, starting from the materials to small capacity cells, in order to predict what could happen when we're looking at future larger capacity cells. So I think that's a very interesting program, and it also shows us, that the DOE, the Department of Energy, is actually concerned about battery safety to be able to come up with these sort of programs and to work with, pre-commercialization that could go out into the market one day to already start looking at them. Are they safe, and what mitigations can we do to them if they're not safe enough?
So that's a federal program, is it, that helps up-and-coming manufacturers evaluate technology?
Yeah, so for that particular program, it's sort of it's a huge one where there are teams that have different battery technologies. These are upcoming ones that have not been really tested in the market yet. So there is that side of the program, and then for us, we are more interested to evaluate the safety side. That's why they brought us in with Sandia, with UMD, and with Purdue, in order to help evaluate these new chemistries and work together to see if we can come up with sort of a document or a standard for these new battery technologies. And hopefully these can be, a way to start changing our mindsets as we think about other new chemistries that are coming out. This document can help to guide future technologies as well. Maybe we should do this sort of testing in order to understand the safety.
So this would be something that would kick in before you went for your UL 9540 testing on a system or a rack or a module level. This is some sort of earlier stage testing that could be done.
Yeah, I believe so. This is for a much smaller scale when you're trying to see how larger capacity cells could behave.
Yeah, interesting. That sounds like a very good program and something that could be very useful, especially at manufacturing stage. A quick question on standards. We're starting to see some regional standards spring up in various parts of the world, and then we're obviously familiar with the UL standards. Do you think at some point we'll get to having some international standards, some ISO standards for batteries that we can follow as a global industry, or is that just too beyond reach?
That would be very ideal for that case. I think for sure, UL is one of the leaders in that. But I understand there are challenges to it depending on country. And different countries, they have different ways of trying to tackle this sort of standardization problems. But hopefully down the line we can have some more guidance, I think, on standards. I think that would be good. And definitely for the lithium-ion side, there are more and more coming up, but there are also different chemistries, as you've mentioned. So one thing that we are thinking about is sodium-ion batteries, how their standards should be different or could be different, because I believe right now they're operating under the lithium-ion battery standards. Perhaps because it's a different chemistry, it should have its own as well.
And what would that be? Just because it's by its nature, it's very much less flammable, or is it? It's probably not flammable at all, is it?
So that's a very good question. So there are not enough safety data to say it. So at ESRI, we are actually making some studies regarding sodium-ion batteries and whether they are the safety testing and. But of course, we test beyond standards. We really want to see, where exactly something can go wrong. But that's something that we are looking into right now, and I do not believe there is enough information around to really say, is this technology safer? So yeah, definitely more research needs to be done for that.
Interesting. Yeah, it's definitely a new technology that we're watching closely because it seems to have a lot of merit for sure.
It's nice to hear about the different combinations, about these new technologies coming out, we're not just staying in one place. We continue to grow and get a little bit better every single day. But yeah, getting on a little bit to sustainability and recycling. Can you talk a little bit about that?
So I think one way we can really think about sustainability for lithium-ion batteries is really recycling, how we can turn it into, a circular economy. Whatever products that we use, can we put it back into a battery, whether it's a second life or even sort of regenerate the materials in order to make the batteries again. So right now, of course, there are not enough cells to recycle. But as we, hear about more gigafactories for batteries being built, definitely down the line, there would be batteries that require recycling. And of course, right now, not so much, but we can always start with manufacturing scraps. That's something that we can at least start, the research on, and we should start now and not wait till, 50 years down the road when we actually need to recycle batteries. That's something we need to start planning, whether it's, sustainable processes, to any infrastructure that needs to be built in order for this recycling project to work, as well as building the talent and workforce. That's something that we desperately need to have, to support these endeavors of whether it's electrification or recycling. That's something that we need to start right now. Something that ESRI, we are interested in. We started a public safety campaign actually. So it's called Be Nice to Your Device. It's like very cute. It's really focused to raising awareness to promote the safe recycling of lithium-ion batteries. So for this campaign, we partner with different organizations. So one of the organizations that we've partnered is called Call to Recycle. So they have a website, an online platform where you can actually go in to search for what's the nearest battery recycling locations based on your zip code. I think that's great because I think a lot of the times, we have batteries that we kept in our drawers forever because we don't know what to do with them. And, with this campaign, easily we can find, actually we can drop this off here, near closest location. So that's great. And then coming down the road, we are actually partnering with Tech Fest Live. There will be an education fair happening in November, and we're also doing a lot of battery collection drives as well. So locations where you can drop off your batteries in a safe manner, which have like instructions, bag this, or if your batteries are too big, please get another size of bags to bag them properly. So instructions, and hopefully that would encourage more people to recycle. And recycling of rechargeable batteries and device, this can definitely help to build a safer and more sustainable world. And I believe the campaign website is called Be Nice to Your Device, oneword.org, and it has a lot of videos, webinars, as well as resources to learn more and hopefully be able to promote it to other people so they can understand how to recycle lithium-ion batteries as well.
One thing's been going through my mind on the recycling side, and I don't know if it's a dumb question, but with all these different technologies of lithium-ion batteries, are any particular technology easier to recycle than the others, or do they all follow exactly the same process and you get the same usable end product?
That is a very good question. Actually, I think one of the challenges is sometimes because there are different battery chemistries, mixing them together for recycling may not always be the best idea. There are always challenges because it depends on the battery itself as well, how it's manufactured. So you may have heard of like black mass, which is whatever the electrodes that you collect after you dismantle the cells. And the way to treat that can be very different depending on chemistry, and it can be sometimes a bit difficult to collect those materials back because they are still stuck to the current collector. Still a lot of challenges, and it's also thinking about the process and also how can we differentiate the different chemistries. And going back to this question about standards, I think it would be good if manufacturers can actually say what technology they are. Like you say, yours is LFP, that's great, but not everyone talks about that technology, and that makes sort of treating or this recycling of the batteries challenging for sure.
Which is good that we're talking about it now, so we can hopefully get ahead of it.
I hope so.
This is good.
Yeah, this is great. Now, you want any more information on UL Research Institutes, you can check them out at ul.org. And as we do with every episode, we end by answering, we get a lot of questions sent in to us from our audience. And actually, if you have a question you'd like to submit, you can send an email to leadingthecharge@power2.com. But today's question, and I'm going to open this up to you, Wan Si, as well. Does temperature impact the performance of lithium-ion batteries? Hot, extreme, hot, cold. The more to the extremes we get, is there an impact on performance at all?
For sure, that's a very huge impact, and I think we heard a lot about EVs unable to start in cold weather, but increasingly we're also seeing hot weather. There are problems of keeping the capacity of the cell. Because there is a temperature range that the battery can work very well, mainly because of the electrolyte. It is a liquid electrolyte, so if it's too cold, it freezes, and then you have problems. So yeah, it is the challenge for low temperatures and high temperatures. Something to think about as an upcoming technology is could be actually solid state batteries. It's something that you can definitely work at higher temperatures, not a problem. And yeah, it is a challenge because something we talk about is like climate change. It's sort of real. It's affecting a lot of aspects of our lives, including how we can use our batteries.
So you mentioned solid state there. Is that a different technology makeup, or is it just a different way of building the battery?
So for current batteries, we have the anode and the cathode, and in between we typically have a separator that so that the electrons don't touch each other. But because of that, we typically have a liquid electrolyte that goes in between, and its main function is to shuttle the ions, for example, the lithium ions from one side to the other during charge and discharge. But for solid state electrolyte or solid state battery technology, this middle portion is substituted with a solid layer, and that solid layer can conduct ions. So there is we don't need the liquid part of the separator in this case.
Understood. Yeah, so that makes sense that you could use it at a lower temperature. Is there a commercialized product available, or is it still in that early stage?
I believe there are a few companies that are working on this solid state battery technology, but it's also sort of very a wide category because there are different solid state electrolyte material that you can use. But yeah, it's heavily being researched on right now, and hopefully at some point we can start to test some really in real cells. And I think something that a lot of people talk about is they can be safer cells. But similarly, like sodium ion, we need to test them to really understand, are they safer? Because I think at the end of the day, we need to understand that these are energy storage devices. They store energy. And if they don't cycle in the correct way, there are other ways that the energy can come out. And I think first we're trying to understand, how is it safer than current technologies?
For sure. That's interesting.
That is a wonderful and I think very complete answer to our question. So thank you very much, Wan Si, and thank you, Tim. And whatever platform you're on, hit the like button, hit the subscribe button, do all of those good things. Leave a review if you have time. And if you want to learn more, as I said before, we'll have links to everything in the show notes, or you can just visit leadingthecharge.io. Now, our legal team wants me to say that any statements or views expressed by the hosts or guests on Leading the Charge are entirely their own and do not necessarily reflect the opinions or positions of POWR2, their partners, or affiliates. And a big thank you to Wan Si for joining us and sharing so much insight on lithium-ion.
Thank you so much for having me.
Thank you very much.
Thank you. And we know your time is valuable, and we appreciate you spending even just a little bit of that time with us. So let's simplify sustainability and keep leading the charge toward a world powered by sustainable energy. See you next time.